The next speaker is Dr. Rick Chalaturnyk from the University of Alberta. He will tell us about his research work on measuring in situ stresses using a reservoir geomechanics pressure meter. Please, Dr. Chalaturnyk.
Thank you, Andrew, and thank you to everybody attending the summit and listening in on all the talks. Thanks very much. Listening to many of my colleagues, say good morning, good afternoon, and good night reminds me of the Truman Show with Jim Carrey. It's kind of interesting. So hello to everybody. So today's talk is a little bit of an update. We started a path a long time ago to try and answer some questions around how to measure in situ stress, perhaps using a slightly different approach. And it's something we've referred to as a reservoir geomechanical pressure meter. So it's a bit of a journey, and look forward to sharing with you some of the results we've had during that journey. A little bit of the background for us, we've had an energy simulation consortium that's ongoing since 2014 till 2019. Sort of first 5 years that had 5 themes that covered all the way from core scale all the way through to reservoir scale, some optimization stuff. And we're just now beginning into the second 5-year phase of something that's an NSERC energy simulation industrial research consortium that's supported by both an NSERC industrial research chair and a collaborative research development grant. Most of our research projects in our group, the Reservoir Geomechanics Research Group, are founded or sort of have as a foundation what we refer to as our geo-innovation environments. They're essentially 4 major environments: GeoRef, GeoPrint, GeoRMT, which is the modeling side, and GeoSurf. So GeoRef is a high temperature, high pressure experimental facility, multi-phase flow. GeoPrint is what we're using to push the boundaries of 3D printing of real rocks. Some exciting stuff. Some of the collaborations, for instance, that Ray talked about this morning around depletion geomechanics and coals. We're actually learning how to print with coal and print fracture systems in these 3D printed materials. GeoRMT is our reservoir geomechanical sequential coupling platform that sort of goes across the full suite of CMG software and then couples to geomechanical codes. And GeoSurf is a large 2.2 meter diameter beam centrifuge that allows us to do some exciting things at high G and some interesting stuff in the first phase with caprock integrity. So in general, these projects have all been focused on sort of 2 classes of unconventional reservoirs, one being the tight oil, tight gas, shale, Montney, Duvernay kind of stuff, Western Canadian focus. And in particular, the other one that we've been keen to have a look at are some of the challenges that are associated with oil sands, and specifically the thermal side. The dotted one you see way on the right-hand side is a ongoing development of iSurf, which is related to the induced seismicity experimental research facility. A lot of our research motivated by this issue that at certain scales, uniformity doesn't work, and that there are geomechanical processes that affect how fluid flow behaves. And so there are, I think a lot of work that's done in the geomechanics world, geotechnical world, looking at properties. You heard Dr. Gusselli speaking about some of those previously, but where our intense focus is really about how those processes impact multi-phase flow behavior, and it becomes quite complex. And so in the box on the right, you'll see a bit of the sort of major areas, all the way from in situ stress all the way through to verification. And so today's talk really is about some of the questions we are asking in the area of in situ stress, but it plays a role in some of the other ones like rock mass properties, numerical modeling, and verification. So if we turn our attention to in situ stress, lots of techniques. People do this, they do this in the oil and gas business, the mining business, geotechnical, strain relaxation, overcoring, very significant method in mining applications to get the full stress tensors, very specialized tools that have been gained for that. More in the oil and gas side of the world, looking at borehole breakouts, hydraulic fracturing. Some in the geotechnical world, kind of foundation engineering design, things like that, have used pressure meters, which I'll talk about in a bit. But there are other ones, acoustic methods, earthquake focal mechanisms, geophysics, seismic. You see some of the compliance tensors, Anderson's, definitions of stress regimes.
Rick, sorry, we're not seeing your screen. You haven't shared the screen.
Well, that's not going to work.
I thought that was my problem. But I got people saying they can't see your screen.
So
okay, good.
how about if I do, so all those words, I will not repeat the words, but I since
go to the slides.
Can you see that all now?
Can you go full screen?
Yep. So I'll just,
yes,
so this was just the chatting about the geo-innovation environments. This was the discussion around the complex interactions of reservoir engineering and geomechanics and the issue around in situ stress. And so I was just talking about the mechanisms for in situ stress techniques. And so the ones today I just want to talk about is in situ stress. And the one I think that's familiar to most people in the audience is hydraulic fracturing. Ray talked about it. Other people have talked about it, is the DFITs, the diagnostic fracture injection test. A lot of work done on that. Lots of discussion. A lot of people have been looking at multiple methods. Ray talked about it. People using G-function methods, ISIPs, fracture closure pressures, using issues around flow regimes as fractures close and trying to use those diagnostic measurements. There's stuff that is sensitive to issues around natural fractures and stress contrast for containment. A bit of a shout out to some folks at the University of Calgary who've, even come up with a thing called DFIT FBA, which is a flowback analysis technique that takes advantage of rate transient analysis. So a great deal of work done in here. This wasn't what we were focused on. What we were interested in was more in the kind of projects that we were taking on. So some of them were, like the ones you see in the bottom left, were permanent changes in permeability that were a result of in situ stress conditions. Dr. Griselli talked about bedding features. So issues that we were interested in is issues around imbibition, fluid imbibition in these bedding planes, and those are all sensitive to stress. Caprock integrity, issues around multiple fracture systems in completions for shales, all sensitive to what you assume is the initial stress state. And even these days now, in the use of DAS and these, being able to capture these real-time poroelastic strains within the material, trying to unravel what these mean, are all a function of that in situ stress state. So I have the habit of saying that if you don't know where you're starting, you don't know where you're going to end up. And so that was really what we did. So we said, well, is there another way we could try and do this? We have some cases where, in fact, if I'm after the minimum stress and the minimum stress happens to end up being vertical in some cases, then I've got to find other ways to constrain the horizontal stresses. And so we looked at pressure meters. And so pressure meters, essentially, for people in the audience, are a packer. Think of a packer, but it's a highly instrumented packer. You insert it in the ground, you inflate it, like you think of a packer, but what you're doing is measuring the internal deformations or the internal radial strains within the tool, so that you can measure, as a function of pressure, you can measure the radial displacements. It's a standard technique in geotechnical engineering. It has its own ASTM test code, and goes all the way back to sort of 1957. Menard did this, and so it's an old procedure. So the kind of data you get from this looks like this. If you look at soft clay, you would, on this axis is pressure, radial displacement, and as you increase the pressure, there are points at which the membrane will now start to push on the material. It will deform it, it'll yield it, you can unload it, you can do unload reload cycles. And what you get is, you can see here the difference. This is 1300 kPa. If I move to weak rocks, I'm going to start getting to 5000 kPa. And if I move all the way over into hard rocks, I get the sort of this kind of the same kind of responses, but they get more complicated and higher pressures, 12 MPa. I get cracking. And for many of you who maybe have done MDT tests in the world, if you do the initial sleeve fracture stages where you try and generate this axial extensional fracture in the borehole wall, these are the same kind of mechanisms that you see. But for us, what we are interested in, and for reservoir geomechanical applications, was to advance this, this capacity, if you like, to get to 40 or 50 MPa soft rocks, weak rocks, through to very hard rocks in the unconventional world. So we called it RGP, a Reservoir Geomechanical Pressuremeter. It really is, the addition of advanced technologies within a pressure meter tool, using some of the stuff that we've learned in the downhole environment, but combining that with some very, well, I would say sophisticated inversion techniques that allow us to actually take those two combinations and compute the minimum and maximum horizontal stresses and their orientation without ever having to do a defit. So we just basically asked a different question. Can we extract different information from this data that's collected? And so over the years, Lang in his MSc did some very sophisticated numerical modeling to look at what that means under anisotropic stresses, characterizing the borehole damage in much stiffer materials as what Lang has continued on for his PhD. And one of the things we learned in the first stages from one of the sponsors was this issue about trying to quantify uncertainty. So I'll share a little bit with you, and that Dongming is working on for his PhD. So our update or our progress is that we've basically worked on RGP1, we call it. It took a standard modified high pressure meter, converted it to wireline, ran an extensive field trial in the first research program from 2014 to 2019, and did some very exciting validation testing in a polyaxial frame in Longfang's facility in China with one of the sponsors, PetroChina and RIPED. We think that it confirmed this ability to take field data, the pressure meter data, and the inversion techniques and actually make these calculations for minimum and maximum stress and orientation. But what we did learn was that RGP2 needed to be changed to a self-boring capability. So I'll explain this in a little bit. You either drill the hole in advance, slide the pressure meter in and do the test, or you actually put in the actual ability to drill the hole in the pressure meter so that it has a much better connection with the borehole wall. And so we did make those modifications. I'll show you a little bit of our early trials with that. And we have had some exciting opportunities to run both RGP1 and what is called RGP2N in the Mont Terri Labs in Switzerland, so much harder materials, and learn something about what that means for anisotropy and things like that. And what we're really moving towards is a fully wireline capable deployment of a self-boring pressure meter tool. It goes down through a core bit, has extensive increases in enhanced surveillance technology, and goes down to depths of 2,000, 2,500 meters. So here's RGP1, pretty simple. Really a shout out to Cam and Situ, the Cambridge folks who build they've been building pressure meters and high pressure pressure meters since for a very long time. And they have been absolutely gracious in their support and have helped us at every stage of the way. But this is essentially what the tool looks like. It has some downhole electronics. You have the packer interval, if you want, the membrane interval, some conversion equipment here to bring in the electronics and the nitrogen gas to inflate the membrane, and so on. And so what we did in a field trial was we northeastern Alberta went in and over 5 intervals, well, 5 tests, basically over 4 major intervals. Did a series of tests, and the one I really want to share with you today is the one called B0T1, which was up in the Westgate Formation. And so in that particular test, slid the packer, the pressure meter down into a pre-bored hole, set it in place, and then started to actually inflate the pressures. And you can see even here from these images that I had showed before, we're already at 14, 16, 18 MPa. And this is the data you get if you take the average data inside the tool. You can generate a curve like you had seen in the cartoons. This is real expansion data for the Westgate. But in asking questions about how to interpret stress from this, what we were really after is that on the inside of the tool, there are really 3 pairs of arms. And so you can actually take each of those 3 pairs of arms and extract that from the data. And what you get is 3 separate curves. So you can see already that if this was a perfectly isotropic condition, all of these 3 arm sets would all lie on top of each other, but they don't. But you can go even farther. In this particular case, you can start to actually look at every single arm. So if you go inside the tool and you extract all 6 arms, you get a completely different perspective of, in fact, how that anisotropic expansion occurred. And you can utilize this data. And so what we did was, we did a lot of work. This is a lot of Lang's work initially and some other stuff. You worry about tool anisotropy, eccentricity, everything else, you correct it. But you can generate these maps that during expansion, you can generate elliptical expansion maps that allow you to actually describe anisotropy, and it's used in the inversion techniques for in situ stress. And so what happened here was develop a procedure that allows you to take all of the arms, the one you're seeing in the animation in the bottom left, is taking all of the arms and using some inversion techniques and optimization and matching techniques to minimize error, but simultaneously on all the arms. And so what you see on the right-hand side would be a fit if you just took the average curve. And so what you get from this is you can get estimates of shear modulus, undrained strength, some other issues around average or mean stress. And so if you look at the test that was done in the Westgate, what you'll see here is that if we apply that technique, I'm just showing you the Westgate. This was that interval of the Westgate, Jolly Foo, and the Clearwater. The black line is the vertical stress. And what you can do is you can take your data from this test, you can run the inversion, and what you will get is you will get a prediction of the maximum horizontal stress, the minimum horizontal stress, and its orientation. And you can look at that relative by just blowing this section up. You can see the maximum and the minimum. And if you run exactly the same process on the averaged curve, you should get a mean stress that falls in the horizontal plane between these, and you can in fact do this, and you can do this for each of the intervals. The other powerful part that comes out of this is actually material properties. You're testing at a scale that's larger than a core scale. At least it's over the meter interval. And so what it allows you to do is actually get shear modulus. So for all of the people who are doing geomechanical work, reservoir geomechanical simulations under different environments, even people who are trying to populate compliance matrices for geophysics work, this gets you shear strain under more realistic in situ conditions. The other part I think that was exciting about this was uncertainty. And this came from some really good due diligence work and some questions from sponsors initially is that sure, if you're going to predict this, but what you need to have is some sense of the uncertainty. And so Dongming has been doing a lot of work. We're continuing in a very big way. But so now we've got ways where we can look at these and we can get uncertainty estimates from the data, given the kind of the way that the testing is conducted, so that we know that, how far out are we? How good was the test? How bad was the test? So exploring a lot of techniques to do that. The validation test was exciting. Really great support from our colleagues in China and Rapid. Very large polyaxial frame, and this allowed us to actually put the tool into let's call it a soft cement. It got very close to kind of a I don't know, for people who might know, a Clearwater formation type material, if you like. Put it under realistic stress conditions. We knew what the maximum and minimum stresses were at the boundaries. And you can see that as the stress ratio changes, as it becomes more anisotropic, you can see this difference in the arms. And this was what was used to do the inversion for that. So that was very powerful test results for both the tool operation and validation. The Mont Terri test in Switzerland, much stiffer, harder class of materials, Opalinus clays. A really exciting opportunity there to run the pressure meter in this sort of BGCA4 location in 2 different orientations. I'll show you some plots in a second. But what was exciting in here was that there is other technology that Dr. Schuster has been running here that allows us to make interval velocity measurements 360 degrees around the borehole. So now the anisotropic response of the arms can be compared now to the seismic or sonic response anisotropically around the borehole. And that was done at multiple locations. You can see in multiple depths, and very, very exciting work. I think that, this is Lang smiling. He was very happy, clearly very happy man doing the testing. So we had tests parallel to bedding, perpendicular to bedding, So some really exciting stuff. You know, so Lang has been working away on this, looking at how shear modulus varies as a function of borehole damage, shear modulus values as a function of anisotropy, looking at these interval velocity measurements. It's a very, very exciting work, and kind of looking forward to what Lang finds, because this is a part of our transition to much harder class of materials, like a Montney, like a Duvernay, that allows us to go in and make these kinds of measurements. A big part of the advance of this, though, and a lot of the learnings from what we called RGP1, was that we needed a self-boring pressure meter. That really, to improve our ability to invert for in situ stress, meant that self-boring was important. So we've actually taken on the challenge of building a tool. We built this ourselves, again, help from Cam in situ, but it has a bit, the assembly of the tool, circulation sub, and it has a downhole mud motor. And so what this does is it's a pretty powerful thing, because now in one location you can make a test, drill ahead, and run a second test, which you typically is a very expensive time labor option for RGP1. So this is just you know, a little bit different picture. You can see the bit. This time the cuttings have to go up and inside and come up the inside of the tool and come out this circulation sub. And so, you know, we built advanced electronics in here, increased resolutions, digital transmission, downhole diagnostic capabilities. And you can see really quickly in this video, just as the bit is starting to penetrate, fluids are actually coming up and out of the sub. So I can, you know, so boot ahead, you can see the material coming out of the sub. You'll see in a minute here as the cuttings are coming out. I think that might actually be Nathan's hands. I think if it there, you can see the cutting. So we've got the ability now to bring the tool to a self-boring capability. The other thing about our update, I guess, which is exciting, is that NAGRA has given us a real exciting opportunity to put a lot of these advancements in practice. You know, very short order, and probably a couple of months. We're about to ship stuff where we've advanced this to 40 MPa, being able to run at 1,000 meters. On board as multiple pressure sensors, temperature. We've really increased the number of radial displacement arms and high resolution, down to 50 nanometers. Accelerometers, magnetometers for orientation, digital signal transmission again, and some really exciting stuff on the surface to be able to operate the test. There are things like hold tests and unload reloads that help you manage measurements around creep, pore pressure measurements, and other things like that. So in terms of a progress, multiple field trials, large polyaxial frame is really showing us that in combination with these advanced numerical inversion, we're still learning a bit about that we are reasonably confident that we can define the minimum and maximum horizontal stresses through a vertical well, and their orientation, and uncertainty estimates for it, which we think is equally as powerful. Intermediate scale rock mass properties are important. A lot of people do in reservoir geomechanical tests. The ability to measure these shear modulus values under in situ conditions, I think is a real opportunity to move some of this simulation work that you've heard many of the colleagues talking about forward. Didn't get a lot of chance to talk about it today, but there is some really exciting abilities to control how you do the test, drained, undrained. You can make certain measurements around transient permeability, pore pressure responses at the boundary during the test. You can do hold tests. You can determine creep properties. Some really exciting conditions that you can impose during the test procedures to extract the kind of data that we need for many of the studies that you've talked about. And I think everything we've seen now, there's every chance that the ability now to deploy this on wireline at substantial depths, self-boring capability with this enhanced surveillance technology is entirely doable. So kind of excited about that part of it, actually. Really keen. Acknowledgements, really energy simulation, formerly the Foundation CMG, has been in our program well before even our 2014 program. Really supported with some early money funding for getting the program going. So really would like to acknowledge their support throughout the entire phase of our work. Number of sponsors in 2014 to 2019 that really were at the core of this work. 2019 to 25, some exciting stuff, even NWMO, which is the nuclear waste folks out of Ontario, but some exciting stuff happening there. RG2 team, a lot of this would not have happened without Nathan. Jacob is a downhole tool design guru, absolutely outstanding. Lang, Dong Ming, the PhD students, Thomas, and on the electronic side, outstanding, and Gonzalo, helping us a lot with membrane technologies and others. And I really do want an acknowledgement for Cambridge in situ. These guys are truly the legends in this field, have been, continue to be. And another fellow, which I forgot to put there, is a fellow by the name of John Hughes at Hughes in situ. You know, these people have led the pressure meter world. Pressure meters have, some fascinating things have been done in this field 30 years ago. And Marl Technologies has really helped us with some of the self-boring capabilities. They were really gracious with their time and their equipment, and allowed us to do some tests on their site. So with that, I'll conclude. Some pictures there of our annual research symposiums and the research teams that we've had involved. So it's been an honor to work with many of them. So a lot of them have already now finished their PhDs and master's degrees, but it's been an honor to work with such a distinguished group. And with that, I'll conclude. Thank you.
Okay, thank you, Dr. Chalaturnyk. We are running out of time on your talk here, so I may try to ask one or two at the most questions. Number one is from Wang Yu Su. Is the friction between borehole wall and packer a significant factor and considered in your mechanical model interpretation?
Oh, you can, but there's been work done a long time ago. You know, we did some just to convince ourselves of it, but that in the mid plane of the packer, where the measurements are made, it turns out not to be an issue. When you get up near where the membrane comes into the sealing assembly, you maybe perhaps could have some issues, but at the mid plane of the membrane, it's not. Okay.
Another question. Radu Busia from Synovus. Can you please comment on the findings in soft rocks with regards to near wellbore measurements versus far field? Wells in near wellbore are most of the time highly disturbed, and hoop stresses impact this behavior. How is your data validated?
Well, that's the whole idea about the moving to the self-boring capability. But even in the pre-bored version, you need the full curve. So if you did partial of the expansion curve, you likely would have some challenges. But by being able to move through the full expansion curve and the unload curve, it allows you to move the response of the rock out beyond the near borehole disturbed zone.
Okay, perfect. Thank you very much. I believe your work, your tool is going to be extremely useful in the energy exploration and development phase, including oil and gas, obviously, geothermal energy, as well as even storage of carbon in the subsurface area. So once again, thank you for your talk, and we'll move on to the next speaker.